The moon is not merely a light in our night sky. It is a stabilizing force, a gravitational anchor that has shaped Earth's climate, tides, and even the evolution of life itself. Yet in theoretical astrophysics, there exists a question that tests the limits of orbital mechanics and planetary stability. What if the moon were to lose that stability? What if, by some disruption, its orbit began to decay and it slowly drifted toward Earth? Under current physical laws, such a collision is effectively impossible. The moon is receding from Earth at an average rate of 3.8 centimeters per year, driven by the exchange of angular momentum through tidal forces. But the scenario of a reversal, an inward spiral, serves as a powerful lens through which to examine how fragile planetary systems truly are. If the moon were ever to fall toward Earth, the consequences would be catastrophic long before impact. Gravitational stress would amplify tides to global scales, destabilizing coastlines and weather systems. The increasing tidal forces would strain Earth's crust, triggering massive seismic activity and volcanic eruptions. As orbital distance decreased, the moon's gravity would eventually exceed the planet's structural limits, fragmenting either itself or the Earth through tidal disruption. The resulting collision, or even partial merger, would release energy equivalent to billions of nuclear detonations, transforming both bodies into a single molten world. The event would erase all biological and geological history in an instant, leaving behind a new planetary object orbiting the sun. This is not science fiction. It is an exploration of astrophysical truth, a demonstration of how every stable orbit, including our own, is governed by delicate balances that can, in theory, be broken. To understand what would be lost if the moon collided with Earth, one must first understand what the moon actually provides. It is not simply a satellite orbiting our planet. It is a fundamental component of Earth's long-term stability, both physically and biologically. The moon's most critical function is stabilization of Earth's axial tilt. Our planet rotates at an angle of 23.5 degrees relative to its orbital plane, a tilt responsible for the changing of the seasons. Without the moon's gravitational influence, simulations suggest that Earth's tilt could vary chaotically between 0 degrees and 85 degrees over geological timescales. Such instability would lead to extreme and unpredictable climate fluctuations, with ice ages and tropical eras alternating rapidly. The moon's gravitational torque acts as a stabilizing force, limiting these variations and maintaining the relative consistency that has allowed complex life to evolve. The moon also governs the tides, a direct consequence of its gravitational pull. These tidal forces are not merely an oceanic curiosity. They have driven the circulation of nutrients, shaped coastal ecosystems, and influenced the evolutionary transition of life from sea to land. Tidal energy also affects Earth's rotation rate, gradually slowing it down through frictional interaction between the oceans and the crust. This process transfers angular momentum from Earth to the moon, causing the moon to slowly recede, the very mechanism that prevents it from falling inward. Beyond its physical influence, the moon has thermal and magnetic implications. Its gravitational effect generates internal stresses within Earth's crust, contributing to the maintenance of geological activity. Some models even suggest that the moon's formation, likely from a massive impact 4.5 billion years ago, helped create the conditions for Earth's magnetic field by stirring the molten core early in the planet's history. From a biological standpoint, the moon has served as a constant environmental rhythm. Many species, from coral to migratory birds, have evolved life cycles synchronized to lunar phases. Even human cultures have used the moon as a natural calendar for thousands of years. Its predictability has anchored human understanding of time and change. In short, the moon's influence extends from the deepest layers of Earth's core to the organization of biological life and human civilization itself. It is a gravitational partnership that defines the very parameters of habitability. Any alteration to this delicate relationship, even theoretical, exposes just how dependent Earth's stability is on a celestial companion orbiting 384,400 kilometers away. Under the known laws of celestial mechanics, the moon cannot simply fall toward Earth. In fact, it is doing the opposite. Each year, precise laser measurements show that the moon drifts away from Earth by approximately 3.8 centimeters. This gradual separation is caused by a complex exchange of angular momentum between the two bodies, the product of tidal interactions. As Earth rotates, its oceans are pulled slightly ahead of the line connecting the planet's center to the moon. This offset bulge exerts a forward gravitational pull on the moon, accelerating it in its orbit. Conservation of angular momentum dictates that as the moon gains orbital energy and moves outward, Earth's rotation must slow slightly in compensation. This is why days on Earth are lengthening over time, albeit by only milliseconds per century. For the moon to fall inward, this exchange would have to reverse. Earth would need to rotate faster than the moon's orbital motion, dragging the tidal bulge behind the moon and pulling it inward instead of outward. However, this configuration is no longer physically possible. The moon's orbital period, 27.3 days, is longer than Earth's rotational period, 24 hours, so the tidal bulge remains ahead, not behind. The system is locked in a configuration that continuously pushes the moon away. There are, however, theoretical mechanisms that could alter this stability. A sudden change in Earth's mass distribution, such as from a massive asteroid impact or an artificial event, could perturb the balance of gravitational forces. A close encounter with another planetary body, or the influence of a passing star, could destabilize Earth's orbit or the moon's path around it. Even then, the probability of an actual collision remains exceedingly low. Gravitational interactions in multi-body systems tend to produce ejections, or new stable orbits long before impact occurs. More plausible than a direct fall is a scenario where orbital decay occurs through long-term tidal friction or energy loss, a process that affects artificial satellites, but not massive, natural moons over short timescales. Over billions of years, when the Earth-Moon system eventually becomes tidally locked, with Earth always showing one face to the Moon, orbital drift will cease. The Moon will stabilize at a fixed distance, roughly 1.5 times its current orbit, far from any collision path. In short, for the Moon to collide with Earth, the laws of physics, as currently understood, would need to be violated or dramatically altered. It would require either an external gravitational disruption of immense scale or a catastrophic change in the Earth-Moon energy balance. Both scenarios lie far outside any realistic astrophysical expectation. Yet, exploring what would happen if the impossible occurred reveals the delicate precision of the cosmic machinery that sustains us. The next question, then, is not whether it will happen, but what it would mean if it somehow did. If the Moon's orbit ever began to decay toward Earth, the consequences would be measurable long before collision. The earliest indicators would not come from the naked eye, but from precision orbital data. Lunar laser ranging, the same technique used since the Apollo missions, would show a measurable reversal in distance. Even a few millimeters of inward drift per year would trigger global scientific alarm. As the Moon moved closer, its gravitational influence on Earth would intensify according to the inverse square law. A modest 1% decrease in orbital distance would increase tidal forces by roughly 2%. While seemingly small, such a change would have profound effects on Earth's oceans and crust. Tidal amplitudes would rise, producing more extreme high tides and coastal flooding in low-lying regions. Coastal ecosystems would begin to collapse under constant saline intrusion. With continued orbital decay, the gravitational coupling between Earth and Moon would begin to impose structural strain on the planet itself. The lithosphere, the rigid outer shell of Earth, would experience growing tidal stresses similar to those observed on Jupiter's moon Io, where tidal flexing generates intense volcanic activity. On Earth, this would translate into increased seismic activity along fault lines and an escalation of volcanic eruptions as internal pressures were cyclically amplified by lunar proximity. The Earth's rotation rate would also begin to fluctuate as angular momentum was redistributed. Even slight alterations in day length could disrupt atmospheric circulation patterns, leading to climate irregularities and more energetic weather systems. The jet stream would destabilize. Hurricanes, monsoons, and cyclones would draw additional energy from the intensified oceanic and atmospheric tides. The moon's approach would become undeniable. Within a few years of measurable decay, it would appear significantly larger in the sky, a clear, haunting sign of gravitational imbalance. The increased albedo from its reflected light would slightly alter nocturnal ecosystems, disorienting animal behaviors that rely on lunar cycles for navigation and reproduction. Human circadian rhythms, influenced subconsciously by lunar brightness, would also begin to shift. As the orbit continued to shrink, the tidal bulges raised on both bodies would grow in amplitude. Earth's crust would flex, fracture, and in some regions, subside under repeated gravitational stress. Ocean tides could reach heights of tens of meters in extreme scenarios. Coastal cities, New York, Shanghai, Mumbai, London, would face recurrent inundation. Before any collision, the moon's proximity alone would render Earth partially uninhabitable. The combination of gravitational, climatic, and geological stress would destabilize every system that supports life. The planet would enter a phase of mechanical and ecological breakdown, a precursor not of impact, but of structural disintegration. At that stage, the countdown would not be to the collision itself, but to the gravitational limit at which the Earth-Moon system could no longer remain intact. Once the Moon crossed the critical boundary known as the Roche limit, the Earth-Moon system would begin its final and most catastrophic transformation. The Roche limit, named after the 19th century astronomer Edouard Roche, defines the minimum distance at which a celestial body, held together only by its own gravity, can orbit another without being torn apart by tidal forces. For the Earth-Moon system, this distance is approximately 9,500 kilometers from Earth's center, or roughly 3,100 kilometers above the surface. As the Moon approached this boundary, the differential gravitational forces acting upon it, stronger on the side facing Earth, weaker on the far side, would exceed the Moon's own structural cohesion. This would initiate tidal disruption. The Moon would begin to fracture, producing a stream of debris, forming a dense circumplanetary ring. The early stages of disintegration would resemble the processes observed in planetary rings around Saturn or Jupiter, except on a vastly more violent scale. Fragments ranging from boulder size to continental in mass would enter chaotic orbits, colliding repeatedly and generating immense heat through friction and impact. From Earth's surface, the night sky would glow with reflected light from the forming debris disk, a final luminous halo before the end. If any portion of the Moon's mass remained gravitationally bound as a coherent object, it would continue to spiral inward, intersecting Earth's upper atmosphere at velocities exceeding 10 kilometers per second. The kinetic energy released by such an impact is almost beyond comprehension. At those speeds and scales, the collision would release more than 10 superscript 3 superscript 1 joules of energy, equivalent to billions of megaton-class nuclear detonations. The outcome would mirror the hypothesized event that created the Moon itself 4.5 billion years ago, the Theia impact, in which a Mars-sized protoplanet struck the early Earth. The resulting energy then vaporized much of both body's crust and mantle, producing a disk of molten material that later coalesced into the Moon. A reversal of this process would annihilate the distinction between Earth and Moon, transforming both into a single molten planetary body. Upon impact, Earth's crust and oceans would vaporize instantly, ejecting a superheated atmosphere of silicate vapor and metallic plasma. Shock waves would propagate through the planet's mantle, melting it entirely within minutes. The release of volatile gases would generate a transient atmosphere composed of silicon monoxide, sodium, and iron vapor, glowing at thousands of degrees Kelvin. From space, Earth would appear as a radiant, incandescent sphere, briefly a miniature star, before cooling over tens of thousands of years. Over time, the molten debris surrounding the remnant planet could coalesce again into new moons, smaller, irregular, and compositionally distinct from the original. Geological history would reset to zero. Such an event represents one of the most energetic phenomena possible within planetary dynamics, a complete planetary merger. It would erase all traces of biological and geological continuity, leaving behind a new, sterile world. The collision of Earth and Moon would not simply end life. It would rewrite the planet's identity itself.